I'm Nikolai, and today we're going to talk about zero-instrumentation observability. A few words about me. I'm initially an ops guy. I worked as a classical meaning system administrator, managed a lot of infrastructures and so on. And now I'm co-founder and CEO at Karoot. We built an open source observability platform that focuses on providing actionable insights based on telemetry data. You can find us on GitHub. Before we start, let's start from the very beginning. What is observability? From my perspective, observability is being able to answer a question about your system. We should be able to understand how the system is performing right now. We should be able to compare its performance indicator over time and understand quickly what's happening, any issues affecting our system, and detect the root cause and mitigate it. And why do we need observability? The first one is availability. We can run our business based on our app or website, but it can make money only when it's available for users. The second thing is performance. We should control performance, such as application latency, because we know that there are a lot of researchers that highlight that application latency can affect even revenue. And the last thing is cost. As your application more performant, it requires less resources, and any significant performance optimization can reduce your cloud costs. I'm a relatively old guy, and I worked in the field when our systems were much more simpler than now. Before, we had applications on dedicated nodes. They communicate with their databases. It was pretty straightforward, and the troubleshooting of such systems was also pretty straightforward. If something goes wrong, you can check the application logs, application metrics, its database, and underlying hardware if necessary. Now we have microservice architectures where we can deal with hundreds or even thousands of services. They communicate with each other. Infrastructures are dynamic now. Nodes can appear and disappear. Our services allocated to these nodes dynamically. So we cannot manage this mapping manually. It's pretty dynamic, and troubleshooting is getting more and more challenging because we should follow the system topology to understand what's happening in our request processing pipeline and how we can make our system observable. The first step is collect telemetry data such as metrics, logs, traces, profiles. We can do it manually by instrumenting our applications with some SDKs. We can deploy a lot of metric exporters or monitoring agents to gather telemetry data in some database, store it like in database such as ClickHouse, Prometheus, and so on. It doesn't matter. And the most challenging part is analyze this telemetry data. We should be able to understand all these telemetry signals to be able to find the root cause. And before we'll talk about collecting telemetry data, let's discuss what we want to know about our systems. I wrote down the list of possible signals, the telling signals about our services. The first one is a service level indicator, such as the number of requests, success rate, and latency. Like super obvious, but we should be able to understand this about each particular service within our system. Then we should understand how the particular service communicates with dependency services and databases. And we should be able to understand like requests, queries, latency. And then we want to know resource consumption and to be able to detect any issues, resource-related issues, such as lack of CPU time, memory, and I/O metrics, super important for stateful applications. Then, since our applications communicate through the network, we should be able to understand what's happening with our network right now. Latency between any services, availability zones and regions, connectivity. Do we have any issues with connectivity in our, like some partitioning in our network and so on. Also, we should understand node level metrics. Then runtime metrics such as metrics about garbage collector and GVM or net runtime, thread pools, connections pool, and so on. We also need to be able to gather logs of every application, every service, and quickly analyze logs if we deal with application-specific issues. And there are two principal ways to gather telemetry data. The first one is manual instrumentation, like we can instrument our applications with OpenTelemetry SDK, or we can use eBPF. eBPF has some advantages, and it's always trade-off. We will talk about it. But eBPF and automatic instrumentation allows you to instrument also legacy services and third-party services, because it's super challenging to achieve 100% coverage of your system with manual instrumentation. With eBPF, it's much easier to achieve since instrumentation doesn't require any code changes. And let's talk more about eBPF. eBPF is a feature of the Linux kernel. It allows you to run a small program in the kernel space, and you can ask the kernel to call your function when some event happens in the kernel or in the user space, such as you can ask the kernel, for example, run this program when some application is trying to establish a new TCP connection. And eBPF itself doesn't provide you with observability or security. It's just a way to run your programs. You should implement this program and run this in the kernel space. And let's talk about fundamentals of eBPF, how we can use our programs and what we can instrument with eBPF. The first approach called kprobes. Kprobes allows you to attach your program to any kernel function call when, for example, TCP connect or file open. And you can attach your program to any kernel function. But disadvantage of using kprobes is that you should track all changes in kernel code. For example, from one version to another in kernel, some functions can be renamed or change their arguments, and you should fix these compatibility issues. The more stable approach here is use trace points. Trace points is statically instrumented places in kernel, such as instrumented all system calls. If you rely on trace points, you have some sort of guarantees that it's more stable API to work with kernel. uprobes allows you to capture a user space program calls, such as you can attach to any process, and the kernel will call your eBPF program, for example, on every OpenSSL write call. It's pretty useful, but it's challenging to use them. Maps allows you to store some values between function calls in the kernel space, and perf maps allow you to share data between kernel space and user space call. And we implemented a lot of eBPF programs for observability purposes. And our monitoring agent called Corroot Node Agent is open source, distributed under Apache 2.0 license, truly open source license. And it's a Prometheus and OpenTelemetry compatible agent. It gathers all telemetry signals like metrics, logs, traces, and profiles. It discovers and instrument all processes and containers running on each node. It discovers container logs and send them through OpenTelemetry protocol to some example, telemetry collector or root. It can also extract repeated patterns from log. It's like it. In few words, it gathers a lot of useful telemetry data about containers running on the node. And let's talk about how the agent uses eBPF. To discover new processes and containers on node in real time, it uses tracepoint task new task. We can see all new processes in real time. We don't need to recheck procfs or something like that. We can be notified by kernel directly and discover and build a model of a node in memory and follow all the changes in real time. We also want to be notified when some process is terminated. And if it's possible, we want to know why. And that's why we use tracepoint or mark victim. We can store some flag in the kernel space that this process ID is marked as victim of the killer. And then when our eBPF program called when the process is terminated, we can read this flag and understand this termination caused by the killer. Also, our agent traces open file events when we use it for log discovery, and we also use it to understand that this particular container works with this disk volume. Also, we want to trace all TCP connections between our containers, and we use a tracepoint center connect, and we can see that this process ID attached this file descriptor to this connection, and the destination of this connection is the following, blah, 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 and so on. Also, we want to detect a packet loss between any containers, and that's why we use tracepoint TCP to be able to calculate the number of TCP retransmissions between any particular containers in our network, because Linux kernel provides only the cumulative total counter for that. Also, our agent is able to capture application level protocol requests and queries. It understands a lot of the most popular protocols such as HTTP, PostgreSQL, MySQL, gRPC, and so on. And to capture this, we use trace points responsible for reading and writing data into file descriptors or TCP sockets. And for performance optimization, we cannot run complicated programs in the kernel space, and that's why we use like super lightweight protocol analysis in the kernel space and more detailed analysis in the user space. Let's look at the example. What's happening when some application is performing HTTP request? The first step, at the kernel, the BPF level, we see the DNS request. We see syscall send a message, and we can understand that is DNS request. Next, we can see that within the same file descriptor or socket, we see a DNS response. So we can capture both of these events and measure latency between these events, and we can understand which domain has been resolved by and which process initiated this request. Then we can trace TCP connection. We know that the process ID, we know the destination address and port, and then we can see that within this TCP connect, we can capture HTTP requests. And then within the same socket, we can capture HTTP response. And this is like just a slide how the kernel space protocol detection implemented. It's just pretty straightforward, stupid, simple program that it detects HTTP method in first 16 bytes of system call payload. And the same code we run to detect that it's like we are looking at HTTP response. And now like these days, most communication, even within infrastructures, are encrypted. And in this case, our previous approach won't work because we in syscalls like send to or receive from, we will see only encrypted data. But using uprobes, we can capture function calls such as SSL read and SSL write in case of using OpenSSL, or Golang specific functions call. And this allows us to capture the data before encryption and after decryption. But it's like a bit tricky to understand file descriptor. And a few notes about how it's implemented, but it's not about eBPF. Our agents just detect that the particular process is using libSSL. So we need to read the binary of, in this case, of shared library to understand offsets of functions and understand OpenSSL version or Golang version, whatever. And then we can attach our eBPF program and captures this request. And few words about performance epoch. When we use eBPF, the Linux kernel provides us with some guarantees because the kernel has a verifier that checks every program before loading, and the program must have a finite complexity. For example, like roughly speaking, you cannot implement loops in your eBPF code. And this is why every program is limited by number of instructions. And this is why we can be sure that our programs will not interrupt kernels for significant amount of time. So we can say that we have guarantees from kernel that our BPF programs will not bring a significant performance impact. In other words, running eBPF on the node will not make your program slower. And in worst case, if your user level program cannot process like telemetry data from the kernel fast enough, you will lose some telemetry data. And from my perspective, it's a great deal for observability purposes. And let's look at the resulting metrics and telemetry, what we can see using eBPF generated data. The first one, we look at our demo environment where we have an application containing many services that are communicating with each other, various databases, and so on. And without any manual instrumentation, we can see the service map, we can understand the latency, number of requests between any particular services. And this map is pretty actual, so it's not generated by some documentations or like if we deploy a new service and, for example, service frontend is starting to communicate with this service, we will see the relevant instrumentation out of the box. We don't need to change anything in this case, and it's pretty useful. If before we looked at an overview, now at low level, we gather information of communication not between services itself, but containers. And that's why we have pretty granular telemetry data, and we can track connections and all telemetry between any particular containers. For example, we can detect that these two services communicate with some latency within availability zone and cross availability zone communication is much slower, and we have all the necessary telemetry data to proceed such analysis. And that's why we implemented this at the eBPF level to be able to capture like granular and accurate telemetry data. Also, we can see all DNS requests made by any particular service. So we can measure DNS latency and errors and anything. And it's super valuable for applications running on Kubernetes, because on Kubernetes, all service discovery is built on top of DNS protocol. But our agent gathers not only metrics, but also it exports OpenTelemetry compatible tracing spans based on the eBPF. So we can easily analyze any outliers and see the particular SQL queries, for example, that are slower than others. And it's like pretty useful because metrics don't allow you to, metrics are just signals, and you cannot understand a particular request. And in case of using traces, it's like possible to. But eBPF-based tracing has some limitations because it's just, I believe that observability tools should be only observers. So they should not change any payload, because in this case, it can lead to like unpredictable behavior. And like I believe that we should only observe. And that's why we cannot bring all eBPF based spans into distributed traces, because we should generate trace ID, and we should like send it from one service to another. And like in case of using eBPF, it's not available. And that's why Karoot supports not only eBPF generated traces, but also OpenTelemetry integrations, because like eBPF is a good starting point and a good way to instrument third-party and legacy services, because it works out of the box. But to be able to see the full picture of any particular request, you need to instrument your application with OpenTelemetry. Also, eBPF is used for CPU profiling, because we can ask kernel to gather some performance counters for each running process on the node and export it. It's like call stacks, and it allows us to explain any CPU anomalies, like you can explain any CPU spike, see the precise line of code responsible for high CPU usage. And also we can compare any anomaly with the previous period and compare the stacks, like using a previous period as baseline. Super useful when you want to explain CPU anomalies. And a few words about how Karoot works. We have node agents, eBPF-based agents that should be installed on each node. They send metrics, logs, traces, and profiles to Karoot. Karoot is a server component. It uses ClickHouse to store logs, traces, and profiles, and Prometheus for storing metrics. Like Karoot is open source, including agents, server components, and so on. And you can run Karoot within your infrastructure and store everything in ClickHouse. It's super useful and much, much cheaper than any cloud solutions. As I said, Karoot is open source. I'm asking you to give it a chance. And it can be deployed in minutes because of eBPF. So in a few minutes after installation, you will see the full picture of your system. It can be run not only on Kubernetes, it also can run on VMs or bare metal nodes. We also have dedicated agent for AWS services. It has built-in advanced database monitoring and supports the most popular databases out of the box, such as Postgres, MySQL, MongoDB, Redis, and so on. It supports all telemetry signals and distributed on the truly open source Apache 2 license. We also have an enterprise edition with additional features and automated root cause analysis. So that's it.